Wagwan people, and welcome back to Kevin Does Physics. Today we're going to be taking an in-depth look at stars. Onwards. Okay, the universe obviously is made up of many different things, such as a galaxy, which is a cluster of many millions of stars. The galaxy the Earth is in is called the Milky Way, and that has approximately 1 billion stars. So these are big things. Stars, our star is called the Sun, and it's basically a place where a large amount of hydrogen and helium go nuclear fusion and emit large amounts of light and heat. We live on planet Earth, and there are many other planets such as Venus and Mercury, etc., and these move around the Sun in orbits. These are formed in a similar way to stars, where gravity pulls together different objects, but the mass is not enough to cause nuclear fusion. And one of the final things we have are comets, which are large rocky icy balls apparently, which travel in elliptical orbits around the Sun in very large radiuses, around 1,000 times the radius of Pluto. So star formation, gas atoms which are lying around in the universe, maybe from a previous solar system, are attracted due to gravity, and this is known as gravitational collapse. As gravitational collapse increases, more and more atoms are pulled into this area, and basically pressure and temperature get to the point where it starts to glow, and this glowing mass is known as a protostar. Eventually, the temperature and pressure of this protostar will become great enough to start the hydrogen atoms fusing together, and this is when we have something called a main sequence star. So a star life cycle, as a main sequence star, during fusion you'll have 4 hydrogen nuclei which will form to become 1 helium nucleus, 2 positrons, 2 electron neutrinos, and 2 gamma ray photons. Of course, when fusion atoms, huge amounts of energy are released. The momentum of these photons released cause an outward pressure, and this is called radiation pressure. And in a star, this radiation pressure, the outward force caused by the fusion, is equal to the collapse of the gravitational field. So everyone's happy, the star just remains star-like. There was once a man called Chandrasekhar who had a limit, and his limit is 1.4 solar masses. And as we can see below this, we have the life cycle of a star. So we start with a stellar nebula, which is just the gas cloud, and then this can turn into an average star or a massive star, depending on the amount of gas we have. If we have an average star, which is below 1.4 solar masses, you get a red giant, then a planetary nebula, and then a white dwarf. If the star has greater than 1.4 solar masses, it will become a red supergiant, then a supernova, and then a neutron star or a black hole, depending on certain circumstances. So next we have electron degeneracy pressure. Basically, in a sun's core, there is a lot of pressure, and these force the atoms together, very close together, and this stops the electrons from moving between energy levels. They're all stuck near the minimum. So this pressure forces them to the minimum energy levels. When there are no more minimum energy levels for the electrons to fill, this causes an outward force called electron degeneracy pressure, and in an average star such as gravitational pressure, this will stop the gravitational collapse, and yeah. A neutron star, as we saw above, is an example of, well, a supernova can turn into, and this is basically where the mass of the degeneracy pressure isn't enough to stop the gravitational collapse. So basically you have a really dense amount of neutrons. Neutron stars emit electromagnetic waves. These can be as pulses, which make a pulsar star. If the star has greater than 4 solar masses, it'll make a black hole. Onto the HR diagram. This was named after Hertzsprung and Russell, who sort of developed it. And this graph shows a relationship between luminosity and temperature. So, for example, your red giants and red supergiants are all pretty hot and highly luminous. Your main sequence stars could take a whole range of temperatures and luminosities. Your blue giants are far, far hotter than your red giants, but we don't really need to worry about blue giants. And then white dwarfs aren't very luminous, but are boiling hot. Like, I wouldn't like to be there. So then we have Wien's law, which suggests that the maximum intensity of light is inversely proportional to the temperature of the body. So if you look up here, cold stars emit more red wavelengths and hotter stars emit more blue wavelengths. Lambda t equals a constant, which is 2.89 times 10 to the minus 3, and this is Wien's constant. Lambda max isn't the highest wavelength we can have, it's the most common. And Wien's law is an empirical law, which means it was based on observations, not like derivative from formulas and stuff. In addition to this, in a similar sort of frame, we have Stefan's law, and what we need to know for this is that luminosity is the amount of energy a star emits per second, r is the star's radius, T is the surface temperature in Kelvin, and sigma is Stefan's constant, and this all produces an equation. So luminosity is basically proportional to T, to the temperature to the power of 4. In life, there are a few issues with these laws. The laws are all fine, but due to issues with wavelengths being absorbed by the Earth's atmosphere, readings from Earth aren't always 100% accurate. That's why we use telescopes mounted on spacecraft, which are outside the Earth's atmosphere, and these allow us to gain more accurate readings. These don't affect the laws, but they may affect the constants. But by now, we're fairly sure that we're fairly accurate. So thank you for watching, and stay tuned for the next episode in the series.